Here we are at the Kennedy Space Center researching past rovers and why man has continually reached for the stars.
The moon, Earth's only natural satellite, is imperative to life as we know it. It orchestrates our ocean's tides, and as Earth's closest celestial body, it is a stepping stone to the universe and beyond.
Already, astronomers plan to create a giant liquid telescope that will collect over 1,000 times more light than the Hubble telescope. That, coupled with the fact that the moon has no atmosphere, we'll be able to see much farther into space than ever before.
The moon can also be used as a fueling station as we transgress further into space. It's 22 times easier to launch from the moon than Earth, and it has ample amounts of hydrogen and oxygen that can be used as fuel.
Furthermore, lunar bases would pay for themselves. The soil is rich in elements such as silicon, aluminum, and H3. H3 is currently priced at about $40,000 per an ounce. It would be easy to mine and transport for equal or less than the cost on the moon.
H3 can provide a lot of clean energy because of its efficiency, which is greater than that of nuclear power plants. 220 pounds could power a large city for an entire year. Silicon can be used to create solar-celled satellites that provide clean energy for space.
Byproduct of these space endeavors are countless technologies, and they can be integrated into our everyday lives. I mean, toothpaste and ballpoint pens are practically everyday necessities.
The Google Lunar Enterprise Foundation understands how important going to the moon is. That is why they're offering a $30 million prize to the privately funded team that gets to the moon first.
They are launching a new era of more cost-effective space exploration that will be funded by private corporations, not just governments. These corporations come from all over the world, and we are glad to see that not only are many countries taking part in this endeavor, but they are working together towards a common goal.
We are modeling it in LEGO with the Moonbots Challenge. We acquired inspiration from lunar rovers and multi-terrain robots. Our goal was to challenge ourselves with the limits of Legos. We wanted to experience the joys of creating, so we prototyped every imagined design.
Our LEGO journey took us through 4 main designs. They incorporated a crab drive for maneuverability, a suspension system to keep the CG constant, which all current exploration rovers have, and an arm long enough to reach over the bumps.
The first robot was based on NASA's new electric lunar rover. However, it was slightly too big and the odd angles of the pivot and the forces made our rubber bands ineffective. It worked better in theory than in practice. This next robot taught us that restricting its motion knocked the robot instead of fixing it. We also learned that without telescoping, the arm was neither stable nor long enough. The following robot was inspired by the Mars rover. However, the necessary simplification nullified our suspension system because the base was no longer parallel to the ground. The penultimate product was a simplification of our original, working design. The suspension system operates on a hinge, with the wheels starting lower than the body of the robot, so it would not hit the bump when the wheels rise to go over it. Because of the angle of this attachment and the requirement to line up all the pivots, we had to use a lot of gears. The placement of the rubber bands was important to maximize their efficiency and prevent the robot from doing splits. The crab drive and the turreted arm were all geared together at a 10.5 ratio, so that the arm was always facing the direction we were moving. This was very challenging to gear. In addition to turreting, the arm was also capable of raising, lowering, and extending. We use a combination of EOPD, touch, and compass sensors, as well as encoders to navigate the field. The touch sensors find the wall for adjustment, and the EOPD centers us on the field's bumps. We had the most trouble with the drivetrain. Complicated manipulators are easy, but the weight of the robot is the drivetrain's own downfall. Also, the suspension system was easily thrown off by CG changes. Another major challenge was gearing around the suspension system. We had 79 gears, and more gears equal more places to skip.
All of our robot designs would have been plausible with larger size limitations. A complex robot takes lots of space. We were too ambitious for the materials available to us.
In the end, we settled on this much simpler crab drive because of time constraints. While the other robots worked, we still wanted a more reliable robot. The manipulators, sensors, and a large amount of code were directly transferred from the previous robot to this one.
With linear programs, there's an order to everything, but LabVIEW is an entirely different way of looking at the robots. I had to reorient my way of thinking, and it was very intimidating. But I learned that different is not always bad.
Each of us walked in with an idea of what we wanted. The robot, the website, the video. The resources, different softwares, programs, and opinions taught me that sometimes you have to compromise in creating a final product that both fits our limitations and exceeds our expectations.
The creators of NXT, RCX, and PowerFunction may have been working for the same company, but they clearly didn't intend for things to line up. Just because things aren't supposed to work doesn't mean they can't. Our robot is proof of that.